Solve question number 27. This is mechanics question. So mechanics, over here we have to prove that acceleration has two components. Acceleration has two components. One is a tangential component and the other is a normal component. So we have to prove it, this equation. We know that velocity vector, when a body moves in a curve, the velocity vector is equal to magnitude of the velocity in the tangent direction. So that is the vectorial form of the velocity when a body moves in a space curve. So when you differentiate it, d by dt, so we have product rule dv dt and tangent plus v d tangent dt. So we have this equation. Now we have the situation over here. This is derivative of the unit tangent with respect to time, but we have a formula. Let's do it using the, I need this value dt ds and ds dt. So in fact, what is this? This is in effect dt by dt. So I will put this by these two terms, but before that we know that the derivative of the displacement or the arc length is velocity. So this is the velocity time, this is the velocity, magnitude of the velocity time dt ds, that is dt d derivative of the unit tangent with respect to time. But we also know from the previous knowledge that this is kappa n. So v kappa n is the unit normal of the curve. So this is dt dt. So we have to replace this by this value, and you see this is the acceleration. The derivative of the acceleration with this velocity with respect to time is the total acceleration is equal to, we left with dv dt in the tangent direction plus now v, and the value of it is v time kappa n. So this v will be multiplied dv dt in the tangent direction, and it is v square. Our kappa is 1 over rho and n. We know that kappa is equal to 1 over rho. So this is the required equation, which is the acceleration of the body moving in a space curve. So when a body is moving in a space curve, we have two types of acceleration: tangential acceleration and normal acceleration. This acceleration is toward the center of curvature, and this is along the tangent. So this is the normal acceleration, component of normal acceleration, and this is component of the tangent acceleration. So this is mechanics, and you know, I think that when a body moves in a curve, then it has two component of acceleration. What is along the tangent and the other is along the normal. So when it is moving on a straight line, so this is 0 then, because the center of curvature is at infinity in that situation. Okay, let's see another question. R is the position vector of a particle of mass m relative to point O, and F is the external force on the particle, then R cross F is m. R cross F in fact is torque. Is torque or moment of F about O. Show that m is equal to dh dt, where h is the angular momentum. So this is the angular momentum, and v is the velocity. So the derivative of the angular momentum is in fact the torque. So let's do it. ये प्रूव करना है हमने. So take the angular momentum. You see h is equal to r cross mv. This is the angular momentum. So I'm writing here, this is the angular momentum. Okay, differentiate it, dh dt. So we have two components keeping m constant. So dr dt cross mv, plus the second term will be leaving r and m dv dt. Okay, now you see this dr dt is in fact velocity cross mv plus r cross m, and you see this is what is this? This is acceleration. So I will write the acceleration over here. Now this term is 0 because v cross v is 0. Same vector cross product 0. Okay, so we left with the value dh dt is equal to r cross mv. But what is mv? Oh, not mv, this is ma. So putting ma as f, it is force in fact. So we proved the argument that the derivative of h, which is angular momentum with respect to time, is in fact the torque. So that this implies that dh dt is equal to, this is m, torque. You see r cross f is m. So what this argument shows, that the derivative with respect to time of the angular momentum is torque. And one parallel argument is this is the angular momentum. So when you differentiate the angular momentum with respect to time, you get the torque. But when you differentiate the linear momentum p, which is mv, so the derivative of p with respect to time is m dv dt. So that is ma, and that is force. So the derivative of the linear momentum is the force. So the derivative of the linear momentum is the force, and the derivative of the angular momentum is the torque. And I think you physicists know these concepts well. but this is vector analysis, so we proved it by the vectorial cross product. Okay, so that's enough for this lecture. We solved 2 questions over here and corrected the third one.